Good afternoon, everyone. Just want to welcome you to this session at the NASCC. We have a new series called Essays by the Experts, and this is our third session on this, and we have a terrific program and speaker for you today. My name is Carol Pavanka. I'm the Director of Continuing Education for AISC, and just want to welcome you here to Nashville to the NASCC. I get to introduce Robert J. McNamara. He's a practicing engineer in Boston for over 40 years, and he is the president of McNamara Salvia Incorporated. He has his BS degree in architectural engineering from Penn State University and his master's from Berkeley. He is widely published, and you can find some of his writings in the Engineering Journal on our website, as well as ASCE Structural Journal, Earthquake Spectra, and other renowned publications. He is an expert in tall building design, wind and seismic engineering, and seismic protection systems. He has applied state-of-the-art innovative technologies to the conceptual design of many structural steel buildings, many major projects, and recently his design includes a 40-story building in the Boston area. I talked to Bob, and one of his passions is fly fishing, and since he's cutting back his practice from 80 hours a week to around 60 hours a week, he's hoping to find more time. With that, I ask you to welcome Mr. Bob McNamara.
Thank you, Carol. I'm not sure how we go with this one. Oh, there we go. Yes, my name is Bob McNamara, and the title of my talk is Designing with Damping. It was picked by someone else. I don't know really what designing with damping means, but that's what one of the promoters of this talk decided sounded sexy, I guess, and might draw some people. So we'll talk about designing with damping. My real ambition was to talk about Skyscrapers 101, so that might be for next year. This talk is basically a discussion on the so-called interest in damping and possibly designing damping systems, or as I prefer to call them, dissipative systems, because we really don't know what damping is. We try hard, and this is the only equation you're going to see from me today, so it's our famous dynamic equilibrium equation. And we try hard to understand what damping is, and there's all kinds of journals that or papers that have addressed the issue, trying to derive what causes it. But basically, it's dissipation of energy under dynamic action, and it appears in our equilibrium equation as the middle term there on the left, the C term, which is a function of the velocity of the displacement variable, and we really don't know what it is too well. We talk a lot about it, and we have fixed numbers. Some people swear by what the damping in their structure is. They think they really know, but there isn't much really good data on what damping is. If you measure it different ways, you get different numbers. And it has a very important part of this equation. You can see it sits there as prominent as the KD term, which is what we spend all of our time on, the stiffness term, the mass term. That's pretty well given by whatever you're doing. You usually don't play with that too much, but as a designer, you spend all your time working out the K part of that term, which is the stiffness matrix, and that is dependent on the geometry, the structural system, the materials, and a bunch of other factors, member sizes, member material types, etc. And we can compute it, and with it we think we can compute the displacements of the structure and so forth. If you're dealing in the static case, and just get rid of those two left-hand terms, you have the static case. So we have confidence in that. If you ask the structural engineer, he can give you rough sizes. He knows how to proportion it. If you ask him what the damping should be, the C constant should be in his structure, I don't think there's too many people that can give you a good idea of what that number should be, other than maybe a percentage of critical. And that's how we categorize damping today as a percent of critical. Steel structures, we usually say they're 0.5% to 2%, depending on what. A lot of different things, but depending. Nobody really has a good number for it. We think we have confidence for a few years, and then we find new measurements that give us a lack of confidence. So it's a very elusive number, and it's also an elusive concept. We don't know what really creates it directly. You say material nonlinearity, cracking, joint slippage, non-structural issues, a lot of different things that we can't compute like we can the stiffness or the mass. So it's a big guesswork, and yet if you assume you have 1% damping, you can get a certain dynamic response. And if you assume you have 2% damping, you get a significantly different response. And if you assume you have 5% damping, you get an even different number. And it's interesting that all of our analysis, when you go to the seismic side of the world, is based on 5% damping. There's absolutely no reason or correlation of that number. It's simply a historical number that's been used from time immemorial since we started to do dynamic analysis. 5%, where'd it come from? No one seems to know. But it's used as if it's truth, and it's really a number, a convenience. The forms of damping that we assume in our equations don't exist in nature. There's no damping that actually fits the CV part of this equation. It's a mathematical convenience. It's a convenience so the equations decompose the way we want them to decompose. So when you're talking about damping, you've really entered a mysterious area. It's one of the reasons why I like talking about designing damping, because you sidestep all of these unknowns, and you do it like you do stiffness. You design the system to provide you a certain amount of damping. What we do know about damping is that it does give us significant response reductions. And this is true especially in other structural fields. Aerodynamic industry, for example, damping is a constant design parameter because it works. And you can test it and you see it working. In structures, as I said, we have this hazy, cloudy vision of what damping is. Unfortunately, the literature in designing damping systems has muddled the picture by calling dissipative systems damping systems, and I do it myself because it's ingrained in the literature since it's been in use for the past 10 or 15 years. And we have come up with the term equivalent damping. And that's the damping that if you add a system, add some kind of damping, some kind of dissipative system, that's the damping that you would get, or the damping you would get related to the response reduction you get from the added system. So it further complicates the issue and throws this designed dissipative system into the concept of damping, which we, again, don't have a handle on. It'd be different if it was like moment of inertia, because you have a feel for that. You know what it is. You can calculate it. This you can't. So one of my problems in discussing damping is this mixed nomenclature that exists. As I said, standard structural design is stiffness and strength. Every day of the week, as structural engineers, that's what you deal with. It's static forces, usually, and it's displacement related, something you can all relate to, beam deflects, etc. Conceptually, damping, we really don't know much about it. We don't have a feel for what C is, the term in the equation that's supposedly equivalent to the mass or the K terms. And what it does is it just groups of whatever response to K that you find in your structure, your actual structure, which is based on dissipating energy. It groups all of that, whatever it is, joint slippage, material nonlinearity, etc., into one term, damping, and it makes it this mathematically convenient term of a viscous damper, or viscous damping for the mathematics, really. As I said, it doesn't exist in nature. We assume values of 0.5 to 2% of inherent damping. This is damping that you find in actual structures. For wind, seismic, as I said, it's a common assumption to have 5% in all of the equations. That's what the response spectrums are reduced to, and again, for no real good reason other than historical. The damping values that you assume are system dependent. If you have a steel axial force tower, a guide tower, for example, no concrete, no nothing else on it, just steel, it's very light, might even be 1/4% of critical. You have a moment frame. Everybody says moment frames are great, they're 2%. Well, look at the plots of what's been done in Japan recently for known test results from damping measurements in the field, and you'll see it's a scatter anywhere from 1/2 to 1.5 to 2. Mostly on the lower sides. Again, it's a mathematical convenience. We can't compute it. So, since it is such a powerful response-reducing mechanism, the way to approach it, I think, is to design systems that, the same way you design your structural parts, your geometry, your sizes, you design a system to provide you with a specific amount of damping. And that you get the reliability of knowing you will reduce the response based on that calculated and designed amount of damping. The equivalent damping systems come in many different forms, and this is another problem with lumping it into so-called equivalent damping or damping systems. They're dissipative systems. Each one dissipates energy in a different way. Friction dampers obviously do it in friction, but they're displacement-based. They're displacement-related. So when they're dissipating energy, the structure is deforming, the same as it is when it's resisting it by the stiffness matrix terms. Viscoelastic dampers, material-dependent, are also displacement-related. Yielding dampers, where you actually yield parts of materials, there's several in the audience, I'm sure, have designed some rather esoteric yielding systems. Again, to dissipate energy, and it's displacement dependent. The viscous dampers are a different breed, shock absorbers. You all have them in your cars. I don't know if, I used to have a car that had very poor shocks, and when I drove it, you really knew you didn't have shocks. Today, I don't think there's too many examples of that, but that was a few years back. But they are velocity dependent, which is really different than what you're used to designing with, because viscous dampers and velocity dependent dampers have their maximum effect when the velocity is maximum. And in most tall structures, which is where we apply a lot of these, the velocity is maximum when the displacements are zero. That has a significant effect on the concept of how to design with these things or how to use them, because when their maximum effect on the structure, the maximum value of the forces in the dampers, the displacements are zero, so the forces due to the usual displacement effects are zero. And that way you can utilize viscous dampers to do a lot of retrofit type work where you're not impacting foundations, for example, and their effect is not additive to the displacement-related effects. Very interesting property and a very important property in terms of utilizing them for retrofit work. Inertia dampers are the tune mass dampers, either with a solid mass or the rage of the day is the sloshing dampers. I was involved with one of the first major applications of the tune mass damper in Citicorp back in the 70s and designed that damper as a, well, it was a tune mass damper, obviously, and it it's considered now, I think, a bit of a dinosaur compared to what you can do today with the multiple pendulum dampers and all of that. Sort of a variation on the theme, but it was one of the first done on a major building. Unfortunately, the literature lumps all these different things into equivalent damping. In other words, how much, if you add a viscoelastic system to your building, how much additional damping do you get out of it that you would see in the equations of motion? And the way that's thought of is the response reduction you get. Let's say you get 10, 15, or 20% response reduction. Well, how much more damping, if you had it in your analysis, would give you that kind of reduction? That's, in essence, what the equivalent damping is. So it really masks a lot of things that's going on. And it's one of the dangers of designing that and thinking of it that way. As a side note, this is one of the areas where the codes are also trying to simplify and come up with codified designs for damping systems, which I think is absolutely the wrong thing to do. These systems are complex, and the simplification of them covers and masks a lot of the important aspects of the systems, and you cannot really design them with simple code approaches. That's just one of my little beefs with attempting to turn the complex analysis of these systems into a formula that has 5 coefficients and the weight of the building on it. It doesn't work. And it neglects some of the very important aspects of the way the systems behave. Thinking about that, one of the ways that I like to think about the dissipating systems, and I have to pause to stop calling them damping systems because that's the way it has grown in the literature and that's the way people talk about them. But I think if you look at a building, simple frame, dotted in dampers as a viscous damping system, shock absorbers, for example, you have your static resistance, which is based on the displacement. You have the dynamic resistance, which is based on the velocity. And so you have these two different resistances that you create. One is created by stiffness and resisting the loads with your structural stiffness. The other is by the motion that happens because of the action on the building creates corrective forces, if you will. In the viscous dampers, they are velocity dependent. In the tuned mass damper, it's displacement dependent, and it's simply a corrective force at the top of the building where the damper, where the mass is. But it's a corrective force. It's not a mysterious damping hidden in the equations. And if you start to think about it as corrective forces, then you can start to think about how you arrange those corrective forces to provide the best system to resist whatever you're trying to resist or reduce whatever you're trying to reduce. And that takes away the mystique of the big C value in the equation, because I still don't know what to guess at the C is when I'm doing these numbers. I always back figure from forces I need. Thinking of it as a spatial vector creates some other interesting concepts, though, because it isn't damping as such, it's a force. And how does that force work? That force has to have a load path. So from the bracing to the structural frame, there is a load path that needs to be respected. I've designed structures where I've seen the load path then not worried about until the last, and the damper will then go along for the ride. It's happy to just ride along with the structure because the stiffness loss of the load path negates the whole effect of the damper. I've seen buildings designed with dampers in them that have neglected it. One of the real aspects of that is we never get the loads that we're anticipating, so the building has never really been tested to see if the damper is going to do what it's supposed to do. But the whole load path is as important a part of the design as the damper itself. And if you put in a soft load path, if you do your analysis based on rigid diaphragms, like we all do for all of our buildings, mostly anyway, It's wrong. Totally wrong, overestimating the effect of what the damping system will do. And that is why I think simplification of these types of systems is just not possible, because you have to know what the forces are going through the systems. You have to know what forces in this case, the viscous shock absorbers would create, and you have to design for them and take that into account accordingly. Otherwise, the performance won't be what you expect. I've seen a well-designed damper system under the action of simulated seismic time history do absolutely nothing because of stiffness loss in the connecting parts. It all gets back to this concept of how they work, though. It's not damping, it's forces. And you've created a set of forces, they have a load path, and they go to the structural frame. So what does that mean? That means that they're not like the structural frame that we design, where we have a frame and we put braces from the ground to the top, and we have columns that go from top to bottom. These do not have to have the vertical resistance stability that your structural system does. It means you can arbitrarily place dampers in space, both in plan and elevation, as long as you take care of the load path. The loads have to get back to where you're resisting them on your structural frame. So you push dampers at various spots, wherever you can stick them in the structure, as it turns out. And you'll see the literature, everybody has them, they turn them into structural frames. They make the structural organization of a damper system, a dissipating system, the same as the structural system. It doesn't need to be. It doesn't have to deliver its own overturning to the base. It goes to the structural frame. The damper system is independent, arbitrary in space, which gives you new freedom in the design. It's kind of interesting. So with that in mind, it keeps you away from thinking about material nonlinearity, things cracking. I mean, I know where a lot of damping comes from in buildings. It's the drywall partitions that creak in the wind. I mean, if you come to a couple of the buildings that I've designed in Boston, I'll give you a real show. They sing. They're like a ship in a good storm. And that's damping. That's dissipating energy. But these systems are different. These are definitely designed. So basically, you have to think about them as how they work. Think about what they're doing to your structural system, not as this equivalent damping. Although I might have to return to that in a bit, because the industry has accepted equivalent damping. And if you're going to do any work in the wind tunnel, they want to know what your damping of your building is, because all the numbers they give you are based on your damping. So you're either going to guess, or if you're designing a system, you're going to tell them what it is, and then you'll get your numbers. Now, as an aside on that, the wind tunnels are doing tremendous business these days in heavy wind areas, because if you have to design these tall buildings for the wind forces that are in the codes, forget it. It's not going to happen. In South Florida, for example, code forces at the 146-mile-an-hour winds are on ocean exposure conditions, exposure C or D by the code, are horrendous. The wind tunnels are giving us back reductions 30%, 40% of those numbers. That's significant. But there's a crux to that reduction. What's your damping? Well, a lot of engineers now are saying, oh, it's 3%. Where are you getting 3%? But they're saying that, and it's absolutely wrong. What's being found on taller, as concrete buildings get taller and taller. I know I'm not supposed to talk about concrete buildings here, but they do exist. And as they get taller and taller, we're finding that the damping is getting less and less. So what's thought to be going up and up on the mega towers in Asia, we're finding that the damping, the measured damping, inherent damping, is less. It's down around 1%, not 2. That's a factor of 1.4 on the response. Simple as that. It's also a factor if you're getting the wind tunnel forces from, or you're getting your design forces from the wind tunnel, it's a significant factor in the reduction of the forces. For example, I just got reduction of 35% of forces on a tower in Florida. That's a huge reduction. Instead of 10,000 kips for the base shear, you have, 7,000, or you have 6,000. It's huge. It makes a big difference in your design. Yesterday I was in New York and I had to tell the architect, you're used to looking at 40-story buildings and the factor is the base shear is maybe 4,000 to 5,000 kips. South Florida, they're doing a design. I said, think 4, because that's the difference in the base shear between New York City and South Florida, Miami. Instead of 4,000 kips, you have, it's actually, the factor on this one was 6. It was 24,000 kips. And that's the kind of difference you can get from the wind tunnel. Now I get a 35% reduction of that force from the wind tunnel because I said the damping was 2% instead of 1. This is a touchy field, I think, and it's all the more reason to design damping systems so you know what the damping is and you can count on that damping and then you can take the reduction. There's a whole host of other things you have to worry about once you do indeed design the system and take the force reduction. But these are the thoughts I have on the whole area of damping design, or what is equivalent damping, and I try to categorize it and cast it into the dissipative systems thoughts and concepts of forces that you create. And that's really what I can leave you with in terms of designing concepts, because that's how they work and that's how you should think of them. And it's an important, and the load path is the other important aspect. So I'll give you a couple examples here of some of the damping designs that we've done. Some of these are a little bit different from what I just talked about, but I think they're interesting. This one I like especially because it was one of our, high-end hospitals with the most sensitive kind of equipment that you can imagine. And if you ask the equipment manufacturers what you have to design for the floor, if you've ever had to do that, you know you can't make your floor that stiff. And if you do, your owner can't afford to make your floor that stiff. So you have to look at different approaches, but this is another area that gets tangled in with, what indeed is the damping and what indeed is the measured damping of the floor. This was a little area in Mass General Hospital in Boston. There was an MRI installation. They were having worries about footfall vibrations like most hospitals do worry about. We designed it for nothing special, the usual hospital live loads. We don't design any of our office or laboratory floors for these very stringent vibration criteria because you can't really meet them with economical designs, and we find that you don't need them. We've done literally millions of square foot of this stuff, and if you have a problem, you might solve it this way. This is if I can point to this, this whole area is a cantilever, that gray area. I think there's a column back here and a column over here somewhere. And this area was the corridor, and the MRI was down in here. And they were having some vibration problems. So we suggested putting in, it couldn't get too much worse. This is where the ambulances come in. So you have vibrations coming up also, not just coming from the footfall. But I like the solution because the solution just is very high-tech and then very low-tech. The tune mass damper was placed right near where the corridor turned and where they actually measured the floor and where we were seeing the response being maximum when footfall was applied at that location. So we put a tune mass damper in, which is not always the best solution for footfall, but the damper was made up between the two beams. That's a section there. I found a piece of metal deck on the job site, and that's the spring in the damper. It happened to be the right section modulus, a moment of inertia. Actually, it wasn't. They put it in upside down first, and then we realized that they had it in upside down. So we had this bottom piece, which is a piece of metal deck, and that's your spring in your two-mast damper, if you will. The mast right here was plumber's lead, and we added plumber's lead until we got the right mast we wanted on the mast damper. And then we taped it up with duct tape. And then we had a Senatech come in and design the viscoelastic damper to give the two-mast damper its secondary damping, if you will. If you look into the two-mast damper design, there's the system design, then there's the two-mast damper, secondary damping to keep it out of phase with the main building or main system. That part, I guess the battery's going on this, but that second part there was the very esoteric, high-tech design by a Senatech to come up with a wire that was in some kind of goo that gave us the damping in the second system. It worked like a charm. And here it was, pieces of nothing that just were the right properties, killed the damping, killed the football vibration with that damper system. It's still working today as far as I know, either that or, as I suspect, more likely, they really don't need that much control, and once we did something, they thought it was fine, and the machines are working great. I mean, that's the way I think a little bit about the medical industry and their need for the high-end precision on their machines. But we did measure the response after we put it in, and it does, two-mast dampers, if you design them properly, can reduce your response by about 30 to 40%, the dynamic part. So that's it, and that's what it was. It was, I forget how many pieces of lead, and then the duct tape to hold it all together in a plywood box. And so that was one high-tech damping solution. And then they refused to pay us for it, so that was a different issue. But this is one I did last year. Another type of damping or dissipating energy problem where there was a design being done in San Diego. Okay. All right. A church, it was called a rock church in San Diego. I don't know too much about it other than I was brought in as a consultant for the design of the two-mast damper. It was, before it was built, the congregation and building committee were concerned about the possibility of the auditorium vibrating, because basically it's a rock church. They really get heavy music and loud and bouncing around, and it was all this cantilevered balconies that the congregation would be on. So they asked us to damp it, or they said they don't want to have annoying vibrations. Well, what is the input? I don't know. What's acceptable when you're bouncing on the balcony singing rock songs? I don't know. That's not in any code that I know of. So I created a forcing function that I thought might be what a rock church would do, and we knew we had to put in a two-mast damper. And so there's an ETABS model, I think, of the balcony and the location of two dampers. And you can see it's a semicircular shape. It's fairly long cantilevers. I forget the actual spans, but the long cantilevers. And they were fairly flexible, but good construction. It was 36 WFs for the cantilevers, and 24s for the infill beams, concrete floors. So how much would it bounce? I have no idea. But I put a person on every one of those nodes, and then I made them bounce up and down, sort of like if it was a rock song. And then I said, maybe we'll accept half of that as a number. And it seems to work. Taylor Devices did the whole design for the two tune mass dampers. It looks now, though, I just found out this morning, that we thought that the two would be fine because most of the action would be in the center. It seems like the side balconies, where we didn't put the dampers, because we did have a design for 4 of them, but of course I didn't want to go for the full expenditure at once. It looks like the side balconies is where all the real action is, and that's bouncing a little bit too much, so we may have to put 2 more in there. But it seems to be acceptable, whatever that is. The congregation says it's okay. So that's another kind of a off-the-side application of a tune mass damper. That's a plot of the response of these people jumping up and down at a certain frequency, say 600 of them at 2 seconds, I think it was. And then the colored response is the reduction that you get with the tune mass damper. And of course the question is, there isn't a number as to what you're supposed to meet. All we knew is we cut it in half, so that should have been good enough, and it seemed to have been. It was a bit of a gamble, but they were willing to go with that, as the floor was made sort of like as stiff as it could. Those were 36-300s. I mean, they weren't going into the plate girders and all that. So that was an interesting example. This is another one that another tune mass damper type application, a very flexible structure, light mass, low stiffness, very low natural damping, and any bounce here is failure, because this is one of these pedestrian bridges, and if they bounce, people won't go on them. You have to close them, and the lawyers take over, and that's considered failure. But they're very light. They have virtually no cladding, and they seem to all have similar spans, the ones I've done. 60, 80, 90, 100 feet is what you end up doing. They all seem to end up, well, this is the sketch we got. You know, this is sort of what Howard Elkus wanted. He said, see what you can do. So I'm sure you've seen other cases like that where you don't have too much information to work with. So I sent it back. I said, I need to at least know something, Howard. Help me. So he sent me back with that. He gave me the height. And then we just went ahead and created a model of what I thought it might be, and did the dynamics on it. And of course, it falls, the frequencies fall right where you don't want them. 2 hertz is just not a place to be, either in floors or in bridges or anything, and that's where it ended up. So that is out for funding now, so I don't know if it'll ever be built, but it'll have 2 tune mass dampers, 1 vertical and 1 horizontal, to take care of those frequencies. And that's just another example of the TMD issues, which I seem to tend to get stuck on because of my original designs in the 70s with Citicorp. But these are small versions. Another example now of the force, which is, I think, a good example of what I was talking about in terms of the forces and the way they can be thought of in space. This building is a tower in Boston we did. It's right at, if you're familiar with Boston, the Prudential Center area. It was a building that was designed in the late 80s, and then nothing was done for 10 years, and then we came back and redid it. And it had a normal 40-story wind system that you would do anywhere. Nothing special. Sort of square building. Outside tube on the perimeter. You can't get much better than that for overturning. Gets transferred to the core at the lower levels, as usual, where you can't have the closely spaced columns. And nothing extraordinary about the building. Designed to liberal but conservative standards, I would say. And we tested it in the wind tunnel, and the projected motions for the building came back significantly higher than we would accept. And it was basically because of the 52-story Prudential Tower next to it. The wind in its predominant direction was peeling off of that tower, and the vortexes were 4.5 to 5 seconds. Well, the period of the building was 5 seconds. So the wind tunnel went nuts with the residents, and we had to come up with a system that would calm that down. And basically, that's the tower. People call it R2D2 in Boston, but it's a Boston Properties project, all office. And this is a vertical organization of the damper system that we came up with, and you can see it's every other floor, simply because we didn't need it every floor. And that's part of that issue, that the force that any one of those little dampers generates goes to the perimeter moment system, the load path. And so you don't need them on every floor. It's not like a brace. It's not like it's carrying a shear. It doesn't need to. It reacts by pushing and giving a shear, giving a load in the opposite direction to the way the building is going. So it's a different issue. And so conceptually, you come up with something that doesn't necessarily look like your usual structure. Structure has holes in it. And in this one, it has what we call a toggle brace. You see that odd-shaped brace, looks like a lambda. That toggle is because the building is stiffer in one direction than in the other, and the toggle amplifies the motion. We're trying to suppress motion, wind response at low response levels, which is a problem because we think we can predict them reasonably well at high response levels. The prediction estimates at lower response levels have an even bigger spread on them, I think. But that's what we're trying to do. So you're dealing with a 10-year storm instead of a 50-year storm. The interstory displacements are very low. The velocity works on the interstory displacements. It's as simple as that. You need to make them bigger. You put the toggle in. It amplifies the movement. Those toggles amplify the movement close to 3 times for what the damper will see, what the shock absorber will see. So it makes the shock absorber cheap. If you had to design the shock absorber for those tiny movements, then the shock absorbers get huge and they get expensive. This makes the brace a little bit more expensive, but it makes the whole package cheaper. In the other direction, the building was more flexible, and we could take advantage of that and didn't have to amplify it. So that's the vertical distribution. That's a look at what they look like locally. Taylor has patented that toggle system. It has a lot of very subtle features to it, especially the out-of-plane capacities. And they work quite well. No complaints. That's what we know about the building. No measurements since it's been installed, but then again, we've had a lot of good storms, a lot of storms with the northwest winds, which is what we're designing for, and no complaints. So that's a solution that was done where we started to distribute these things spatially, and you can see in the plan, there's not what you might think of as a symmetrical organization either. You can do what you want in the plan. Again, it's throwing forces back to your structural system to correct the motion it's going through. And that's sort of the nice thing about it. And so you can play with that. I've seen a couple of papers now from Southern Cal professors that have used them strictly to take care of torsion problems. Torsional motion problems. So you orient them just for the torsion. Don't worry about just the translation. It's a different way of thinking from our usual presentation of these systems, and it really gives you a lot of freedom. I think I've worked on them for seismic damage control, and I think the appropriate approach is simply to put them in the bottom floor. Not so much like a isolated building, but a seismic damped building, which I'll show you, I think, next. This is in the paper that's in the CD, I think, and you can see there's good reduction. That's basically what's there for the different directions. This was a case for seismic damage control, again using viscous dampers. New airport terminal in Boise, Idaho. Says the old classification was 2B, I think. So it's a moderate seismic zone. But it's one of your terminal type buildings, so you have large glass walls. Mainly designed, the Taylor convinced the architects and engineers before I got involved to consider a damage control system, and then we got in and did that. It was then designed trying to limit displacements. Your usual airport terminal roofs with very sparse lateral systems, if you will, and even sparser in Zone 2B type exposures. That's the finished product, I think. Basically, we did a 3D model, and we put in dampers in that wall. The frames, they're a little misleading there. Those are 52-foot spans, so they're very flexible moment frames that they had in the glass wall along the plane, and then we had braced frames perpendicular to that wall up to the roof, and it was designed locally then for the spanning from the roof to the ground. But what we have here is what those two dampers that were put in that direction have done. And this particular plot, which I always find interesting to do, this is for one-time history. And that sort of gets back to that comment earlier about trying to do this with one equation with 5 coefficients. Not a chance. This time history shows you what's going on for one-time history, obviously, but it's scaled. It's the best we can get for time history analysis, and it shows you the composition of where the forces go. And actually, you'll find that in some of these cases, the shear that's generated by these dampers as it's going back to the structural system is bigger, can be bigger than the shear that's originally created by the time history without the dampers. It's an interesting aspect of how they work. And this is why I think you can just put them in on the bottom level and it damps out or forces out the response. This approach here cut the expected displacement response in that direction by about 50% with those dampers. Major airport terminal, the whole package cost about $100,000, and they bought all that protective system with that. Not only did they buy it in this direction, they bought it in the other direction. So it says there 30%, I'm sorry. But the cost was $100,000. In terms of the protection that was brought. And it wasn't one of like, if you were doing this in California, you would have a much higher intensity of design level in terms of the base motion, but you'd also have a lot more things you're looking at. The authority really just wanted to have, it was more of a political solution than a structural solution, but as it turned out to be a fairly good structural solution, I was surprised by the end results. There's some plots of the before and after. So you can see you get similar response, but the peaks are they're all reduced by 30% or so. And that's just what those. This is really not part of this talk, but I forgot to take it out. This was one that we're looking at in one of these design competitions, and the race for the tallest, 107 stories. That will have twin mass damper on the top, no doubt, if it ever is built. The do these design competitions, and they want to have the tallest in the world, and then somebody else beats them, and then they have to do another design competition, I guess. But this was 107 stories, so again, looking at the... But I also like this solution. This is what you're given when you go to the Hyatt in San Francisco on Union Square. And they hand you this card, and they will give you earplugs if you want. This is alternate to damping solutions. That building is 40 stories. It's a steel frame, and it sounds just like a boat. And it creaks and moans at 5 seconds in one direction and 4.8 in the other. And I sit there and measure it, of course, when I stay there. And that's how you can solve it without spending any money. So that covers my talk on damping systems, and if I leave you with anything, it's remember that load path. Thank you. Any questions? Sure. The question is what testing is done to correlate the analysis. To date, none. There has been testing in universities. For example, the toggle brace system was tested in the usual plane frame situation for maybe a 5-story frame or something like that. I forget exactly what the tests were done. The dampers are very reliable in themselves. I don't think there's any worry about that. The issue of putting them into buildings is the real important issue because, for example, a test in a plane frame, 2-bay frame, is not going to uncover the load path issues. But there have been a lot, the dampers themselves will be tested to a spec for the job, but there aren't any full-scale tests any more than there are any good measurements of existing damping that exist, and it's all being based on that same kind of projection. The tune mass dampers have been measured in storms, do reduce the response as predicted. Whether the storm is what it's supposed to be is one issue, plus or minus whatever that number is, that can be big. But the tune mass damper, for example, on Citicorp does give the response reductions that were expected for that building. And I think there are other measurements. I don't keep up to the latest in the big tune mass dampers. I'm more interested in distributed damping systems these days, but I do know Citicorp numbers were verified. Yes. Oh, okay. That I didn't think so. The one cost that was quoted was the terminal cost there were only I think there were only like 12 dampers in that terminal. I'm not sure the total number, but there's 4 in the face. There was 12 altogether, I think. 4 in the longitudinal face, and then there were 4 lines of transverse bracing in there. But that was the cost of the damper. It's not the cost of the frame or any of the structure, the bare structure. It's the cost of just the dampers installed. That's according to what Taylor gave me from that project. It was very low. No, it's Taylor Devices. That's where the cost number came from also. And they hired me to do the analysis and the study as to what was needed. So I was sort of like a sub-consultant to them on that. I don't see where that comment came from, but I think I know the person. No, I didn't do it for nothing. This gets back to almost some of the things that Ron was saying. I believe in complexity, but I believe in getting paid for it too. And there's no way that you do this kind of work in your structural fees, or even close to it. These projects your fee will equal your structural fee easy on tall buildings. It's because you do, the one in Boston, for example, the wind was easy. That was no problem to come up with the system, to analyze it. We actually had the wind tunnel give us time history windows of wind from the tunnel in the directions we wanted. You get into all of the esoteric scaling problems and time problems, and that eats up a lot of money and time, but not of my interest. The seismic design of the dampers in Boston, all those dampers were controlled by the seismic design, actually, because the force levels in the dampers, in the toggle brace, if you reduce the motion or amplify the motion by 3, you amplify the forces by 9. It's squared. Whatever you're amplifying the motion by, you're squaring the forces by. So the forces are big in those toggle brace systems. And then when you go and do a responsible time history analysis for various earthquake scenarios, that governed the design of all of those dampers. And that took a tremendous amount of work, because in that project, you're sitting on 200 feet of Boston blue clay. So we had to do the site analysis, we had to do the filtering analysis to get motions up to the base of the building, and then you could find out maybe what the envelopes were for your dampers. But all of this is envelope stuff. There isn't a force you design for. You have to take a step back and know that you really, on the wind side, I've heard that the wind predictions could be plus or minus 30% on the velocity. Well, that's square that when you're talking about the forces. And we all know what the seismic gray area is. So you envelope these things. You get into problems on the design of that one in Boston with the horsepower rating for the damper and the heat that it's going to generate, because we put them in stair towers. You're not fireproofing them, so you're not going to use them for the structural safety of the building. That's one of those other issues I said you have to address if you're really going to start to take these force reductions. In the wind tunnel, you don't have to do that. You just say, well, I think my damping's 2%, and you got it. No, I can tell you my fee on that was a quarter of it. Okay, on that Boise. On Boston, it was not a quarter of that. Because once you have to do the sophisticated seismic analysis, that eats up a lot of dollars. The Boise was easy because it was the same as Boston, but the foundations were simple, so we didn't have to do all of the filtering and all of that other analysis. And the client didn't want it. Yes?
If you're not using equivalent damping, how do you do a preliminary design?
Oh, you have to use it. I try to point out the problems of thinking of it as equivalent damping, which you just get into this 1%, 2%, 3%. I mean, when I did Citicorp, we were aiming at 4% equivalent damping, and we got like 3.8 or something. I think it's a very convenient concept. But when you see it used in seismic design, where they simply take the equivalent damping and divide the spectrum by it, boy, you've made some big steps, and you really haven't accounted for a lot of things along the way when you've done that. That's what I don't like. I like to be able to say, you've enveloped the situation properly with all of the uncertainty that you know on 1, the ground motion, on 2, the scaling, on 3, okay, now you got to pick 3 records or 7 records, and how many directions, and how do you combine them? By the time you're done with your input, you have a pretty big spread, and that's what you have to keep in mind, I think. Yes? I've never considered the cladding in the sense that I'm calculating loads. I've seen its effects in measurements where, you'll see the degradation of the period with movement, but I mean, there's very little guidance on analysis versus the code. If you take, again, steel buildings are pretty easy, straightforward, because there's a lot of the uncertainty is not there in terms of the material property, the modulus, for example. But concrete has the big unknown of cracked versus uncracked. And cracked versus uncracked makes a world of difference. And how you do nonlinear time history analysis on a cracked versus uncracked shear wall system is way beyond what nonlinear time history analysis can do. And people will do it. So, then to worry about the cladding is a next level up of priority, I would think. It's not that important. It goes first anyway in seismic. In wind, I don't see that it makes that much difference because it's all jointed. It's not, if you have precast on it, the connections are only worth so much. If you have a curtain wall system, it's jointed, so it doesn't contribute that much on a tall building. I think it's more important in buildings that are 5 to 15 stories. That's where I've seen bigger numbers in the period discrepancy between calculated period and measured period. You always see the measured period being much smaller on those type of buildings than the calculated period. But I don't know, when you say the code tells you to take it into account, I don't read it that way. I think it's engineering judgment again, and if you're doing seismic, the cladding is damaged, usually. If you're doing protective design, that's a different story. And that's part of the reason to do the protective design, is to protect the cladding or contents. Oh, yes, you take the mass, but the stiffness, no. Right. Anyone else? Yes.
I've got a couple of questions. Do you use linear or non-linear fluid viscous dampers?
Boy, testing my memory. On the Boise terminal, they were linear. On the, I think, we do fool around with the linear versus nonlinear, especially if seismic is governing the design, and that's an important aspect in the design, in the specification of the damper, because you can cut off the tops that you have to design for by specifying. That's a very good point. It's an interesting design point, because you get your analysis back and you see all these huge forces and you say, okay, but if I do this with the damper, you can specify that nonlinearity you want, and those peaks go away. So I don't think you're fooling yourself with numbers there, but it's a good design concept to use when you're doing that. There's a paper that was written by a group of people that I reference in this paper. In fact, this paper doesn't match this talk too much. There's certain things in there, but some of the concerns are in there. But it's a compilation of 5 or 6 authors on the state-of-the-art of the seismic design of these things for damage control, and I think that's a pretty good paper to look at.
The second question is regarding future inspection of dampers, especially in high-rise. It seems that they could eat square footage, and I know that there is a code requirement, I know that at least in high-rise, there is a requirement that you inspect them every so often or be able to see them out. So I know that it's something that we already have.
The ones in Boston Tower are in stair towers. You can see them. They are not counted on for strength reduction or force reduction. They are serviceability solutions. So there's no fireproofing and there's no inspection required. If you're doing seismic damage control, and you're taking your base shear that the code says is 5,000 and you're making it 2,500, you better have inspection, yeah. And those are the kind of things that have to happen. I don't, the fireproofing issue is another big issue for this. And people have complained about tune mass dampers and not, some people want to take the advantage of the response reduction, which is really a force reduction on your system when you finally look at what's happened, elastic forces or displacement related forces, then you get into, well, do these need, do they have to have the fire rating that the rest of your structure has? And then it really gets to be a quagmire, because how do you fireproof it? Maybe you just fireproof the room, I don't know. But I haven't been involved where we've been taking the advantage of the strength force reductions that you can get from seismic. Seismic, or wind, you aim for 2 to 4% of what you put in of equivalent damping. Seismic, 15 to 20% gives you a nice reduction and a nice design and a nice damage control. So they're the two ranges that you work in, and they're two different, they call for them two different solutions. Yes. that was an alternate solution. No, the John Hancock building has nothing to do with the Prudential Center. Thank you. Okay. So any other questions or? Thank you.